Okay, so today we're going to review for exam number 3. Um, I'll have some general comments regarding the exam, how it will be the same as previous exams and how it will differ a little bit. And then we'll go through the topics of each chapter and talk about some of the things that you need to know and skills you need to have related to those topics. So exam 3 is generally viewed as a little bit more difficult than exam number 2. The average tends to be maybe a couple of points lower, not too different, but it's going to be the same format and the same length as the previous 2 exams, 20 multiple choice questions worth 3 points each. And then the remaining 40 points will come from short answer questions. On our last exam, we introduced some new types of short answer questions, the ones where we predict the products of reactions, provide reagents for converting starting material to a specific product, and then draw curved arrow mechanisms for reactions. And we will see all 3 of those types of questions on this exam as well, because we have many reactions we've been studying in these 3 chapters, and those sorts of problems are well suited for testing your knowledge of the reactions. There's going to be a new type of short answer question. I mentioned this briefly in class on Monday, and that is a multi-step synthesis problem where we'll give you a starting material or criteria of types of starting materials. We might say, since we've told you that alcohols are readily abundant starting materials, we might say starting with alcohols of 3 carbons or less, show how you would synthesize the following compound, and it would be a multi-step process that you would have to design. The book gives you some strategies for how to do this, as well as practice problems. This is a topic we're going to address in more detail on Friday, but you'll want to be practicing it before then in order to be ready for the exam. So there are homework problems on multi-step synthesis that I suggest you work. Our TAs are going to be going over multi-step synthesis strategies and problems in their recitations this week, so I would encourage you to participate in those. They record those recitations, so if you're unable to be there at the time that they are on Zoom, then you can view the recordings. But you definitely need to practice multi-step synthesis. The only way to get comfortable with designing the strategies and writing out the multi-step synthesis routes is practice. So make sure you do that. Of course, there are many reactions in this section of the class. And a good way to keep the information straight with the different reactions is to make flashcards. For each reaction we've learned, you could make 2 types of flashcard. One where you have a starting material and a reagent on the front of the card, and then on the back you would have the product of that reaction. And then the other type of card would be one where you had the starting material and the product on the front of the card, and then the reagents on the back. And those flashcards will help you learn the details necessary for the first 2 problems you'll see on the short answer section, which will be predict the products and provide the reagents. The flashcards won't help you learn the mechanisms, and so for learning the mechanisms, I suggest writing the mechanisms out repeatedly. Initially, you might be memorizing things, but by the end, you should be able to predict what step is going to come next based on your knowledge of the chemistry involved. So once you can look at a starting material and a reagent and predict the first step, and then once you draw the first intermediate, if you can predict the second step, and so on, that's when you know you have a good understanding of a mechanism. And usually that takes writing it out and then also just reviewing the reasons for those steps, which we've gone over in class, And so hopefully they're in your class notes. If not, you can go back and rewatch the class videos to get an understanding of those mechanisms. So those are some of the general points that will help you for exam number 3. Even though it is a challenging exam, even though the average does typically go down by a couple of points relative to exam 2, you shouldn't be scared of it. There are every year several students who do better on exam 3 than they do on exam 2. So hopefully you'll be in that group. So with that, let's go to chapter 9 and go through a list of the key topics from chapter 9 and the things that you would need to know in regards to those. So chapter 9 is entitled Alcohols, Ethers. Boy, the chalk broke already. And related compounds. Okay. And so we learned about, in addition to alcohols and ethers in this chapter, we learned about thiols and sulfides briefly, which are analogous to alcohols and ethers, but have sulfur atoms. And then we spent some time talking about epoxides as a special type of ether. So most of our chapters start out with nomenclature. And as it was on exam 2, most of the nomenclature testing on exam 3 will be indirect. You'll see the names of compounds in the instructions to problems or in the answers if it's a multiple choice problem in some cases. So you'll need to be able to interpret those names, interpreting nomenclature, and there may be one or two direct problems on nomenclature. So not a huge part of the exam, but something that you do need to pay attention to. So some of the things we learned about nomenclature, alcohols have a special priority. Alcohols were the first type of compound we studied that have their own suffix in IUPAC nomenclature. And whenever you have a type of compound with its own suffix, it has some priority over the functional groups that are only listed as prefixes in IUPAC names. And then we had our epoxide naming system as well. There were 2 ways we had of naming epoxides. If you have to name an epoxide, well, there were 3 ways, but there were 2 more common ways, and we talked about that in class. If you have to give a name for an epoxide yourself, you can choose either of those 2 naming systems, but you should recognize how to use both of them, because if I write the name of an epoxide on the exam, I could use either the epoxy alkane system or the oxirane system. Then we went on and talked about interesting alcohols, ethers, and epoxides. And whenever we do this, for exam purposes, you want to focus on the compounds that where we discuss their structure and their function, and we connect the 2. And in this area of the class, the compounds where we did this were the crown ethers. We talked about how crown ethers are synthetic ionophores. We talked about how they form host-guest complexes with cations and what that enables in terms of SN2 reactions. So that's the topic you would need to focus on for the interesting compounds. So then we went on and talked about the preparation of the compounds that we studied in this section. And the key reaction we learned was the Williamson ether synthesis. Okay. Which is simply an SN2 reaction. So it's a type of reaction that we've learned before. The key thing, really 2 key things in regards to the Williamson ether synthesis. We have to deprotonate an alcohol to make an alkoxide, and you should know what kind of base would be used for that. And then that alkoxide reacts with an alkyl halide to make an ether. And when we have an unsymmetrical ether, and there's two possible combinations of an alkoxide and an alkyl halide, usually one is better than the other. And we had an iClicker question on this subject. And so you should be able to identify which of the two combinations of alkoxides and alkyl halides would be better for synthesizing a given ether. Okay. And then epoxides are also synthesized by Williamson ether synthesis, but it's an intramolecular reaction using a vicinal halohydrin, which we learned how to make in chapter 10. Okay, so that was the main reaction for preparation of the compounds that we have studied in chapter 9. So then the remainder of the chapter was spent discussing the reactions that these types of compounds undergo. And as you know, there's several of those reactions. The first one we had was dehydration. Okay. And then there's two methods of dehydration. And as alkenes are the products, one important thing to note about the dehydration is that the dehydration reactions will follow Zaitsev's rule. We learned that in chapter 8, that more substituted alkenes are formed faster than less substituted alkenes. And the dehydration reactions we learned in chapter 9 follow that pattern. So the first one was the acid promoted dehydration. And remember, it requires one of two acids. We have to use either sulfuric acid or toluene sulfonic acid. Okay. And if you understand the mechanism, you should know why that is the case. Why the dehydration will not work with our HX acids. They will undergo a different reaction with alcohols. So some details about this reaction that are important. And if you understand the mechanism of the reaction, then the details will make sense. These reactions are E1 for secondary or tertiary alcohols. They are E2 for primary alcohols, the ones that cannot form carbocations. So the mechanism depends on the type of alcohol that is formed, that is used. We're using a weak base in this dehydration, so the E1 is the normal pathway, except when it cannot occur. More substituted alcohols will react faster. We also learned that this reaction is endothermic. We're breaking two sigma bonds and replacing them with a sigma and a pi bond, so it's endothermic. But we also talked about how we can use Le Chatelier's principle to drive a dehydration reaction to completion. And then we introduced the topic of carbocation rearrangements. Because there is a carbocation intermediate in this reaction, there are carbocation rearrangements that can occur in this process. So that's something we have to look out for. Two things to remember with carbocation rearrangements. Number one, it will only occur if the rearranged carbocation is more stable than the original carbocation. And number two, it will only occur via shift of a hydrogen atom or an alkyl group from one of the adjacent carbons, one of the beta carbons adjacent to the positively charged carbon. So the two things to look for carbocation rearrangements, which can happen in any reaction that has a carbocation intermediate. And then we learned our second method of dehydration involving phosphorus oxychloride and pyridine. So rearrangements are often undesirable. Many times we want the product, the unrearranged product in a reaction. And so by using phosphorus oxychloride and pyridine, we have a different method of dehydration, a different mechanism, and so there's no carbocation intermediate, and therefore no rearrangements. So the key thing here is recognizing that the phosphorus oxychloride and pyridine is an E2 reaction, and therefore there are no rearrangements. So you should know the mechanism. Phosphorus oxychloride, like some other reagents in this chapter, has a phosphorus atom where all of the bonds are to more electronegative atoms, so that phosphorus is highly electrophilic, and that results in it being able to be attacked by weak nucleophiles such as alcohols. Okay. All right. So the next type of reactions that we learned about were reactions involving alcohols and HX. Remember I said that HX does not promote dehydration of alcohols. It promotes substitution because the conjugate base is a strong nucleophile, so we see substitution with our HX reagents. So a couple of details here. Much like the acid-promoted dehydration, you have different mechanisms depending on the type of alcohol. So here we have SN1 for secondary and tertiary, SN2 for primary alcohols. And this is a challenging topic to understand because in all other instances that I'm aware of, SN2 reactions are faster than SN1. But when alcohols react with HX, the more substituted alcohols react faster, and the SN1 pathways are faster than the SN2 pathways. So it's the only reaction I'm aware of where that happens. It's a difficult concept to understand and to explain. My best explanation is that the leaving group in this case is water, which, although it is a good leaving group, it is the poorest of our good leaving groups. And so presumably the fact that it is the worst of our good leaving groups slows down the SN2 reaction more than the SN1. And that's what allows this inversion in rates where the more substituted alcohols react faster than the less substituted alcohols. We also taught you that the rate depends on HX. The stronger the acid, the faster the reaction is. HX is acting as an acid before the rate determining step, so it does impact the rate. And there was a bit of information that was important here. The slowest type of alcohol, the primary alcohol, and the weakest of our strong HX acids, remember HF doesn't participate, but when you have that combination, the weakest acid that is reactive and the slowest alcohol, you have to use a Lewis acid, which makes the alcohol an even better leaving group than the protonation does, and zinc chloride is the Lewis acid that we use in this particular reaction. Okay, so this is a substitution process, and when we have a substitution reaction, we need to pay attention to the stereochemistry, meaning do we have inversion or do we have racemization? And that depends on the mechanism, of course. When it's SN1, we're going to see racemization. When it's SN2, we're going to see inversion. Okay. And then also, in the instances where a carbocation forms, we do have to be on the lookout for rearrangements. So because we can have rearrangements with secondary or tertiary alcohols, because we would have racemization in those cases, organic chemists have developed other ways of converting alcohols into alkyl halides. And I'll just tell you right now that these other methods, because they give clean inversion of stereochemistry and they have no rearrangements, they're going to be very useful to you on multi-step synthesis problems if stereochemistry is something that you have to control. So we learned that thionyl chloride, or SOCl2, combined with the weak base pyridine, is able to convert alcohols into alkyl chlorides. We learned the mechanism for that reaction, so it's something that you should be able to draw and understand. And this reaction proceeds by inversion, and there are no rearrangements because both of these points come from the fact that there's no carbocation intermediate in this reaction. Okay? But since it is SN2, it also doesn't work with tertiary alcohols. It only works with primary and secondary. Then we learned about phosphorus tribromide, or PBr3. So that's a reagent that will convert alcohols to alkyl halides. Same principles apply. Clean inversion, no rearrangements, no carbocation. Because it's SN2, it only works with primary and secondary alcohols. Then we learned of a third way of converting alcohols into a good leaving group, and that is making alkyl tosylates. Okay. So we learned the reagents for this, tosyl chloride and pyridine. We learned the mechanism for this reaction. And then we learned why this was important. This was the one way of converting an alcohol into a good leaving group that proceeds with retention of configuration. We are not breaking the carbon-oxygen bond in the alcohol to make a leaving group when we make an alkyl tosylate. All of our other methods involve breaking that carbon-oxygen bond. These two methods right here, as well as this one. So we had iClicker questions that explain why this is useful, depending on the stereochemistry you want in your final product. Sometimes you want to convert your alcohol into a good leaving group with inversion, in which case you'd use one of these two methods. In other cases, you need to convert your alcohol into a good leaving group with retention, in which case you would need to make a tosylate. Okay. All right. So the next we learned about ethers, and ethers. They are less reactive than alcohols. We talked about that. They only react with HBr and HI. So in the same way that alcohols would react with these acids to give alkyl halides, ethers will also afford alkyl halides, but because there are two alkyl groups in an ether, there are two parts to the mechanism and two alkyl halides that are obtained. And if it's an unsymmetrical ether, the mechanism of that substitution process might be different. The example we gave in class was one where one of the substitutions was an SN1 process and the other one was an SN2 process. Okay. And then there's an alcohol intermediate. So there's two parts to the mechanism. We form one of our alkyl halides and then an alcohol intermediate in the first part. And then in the second part, that alcohol intermediate is converted into our second alkyl halide. Okay. So comparable, analogous to the reaction of alcohols and HX. Okay. Then we learned about thiols, the sulfur analogs of alcohols. And key things with thiols, we learned that they cannot hydrogen bond, and so they have lower boiling points than alcohols. The SH bond is less polar than the OH bond, so no hydrogen bonding. We learned a couple of reactions of thiols. We learned that you can oxidize a thiol to obtain a disulfide. And we learned reagents for that. We didn't learn a mechanism, so in this case, you just have to memorize the reagents. And then we learned that you can reduce a disulfide to afford a thiol, and we learned reagents for that reaction as well. So those reagents just have to be memorized. Those mechanisms are a bit complicated and beyond the scope of the class, and so we didn't learn them. Then we learned about sulfides. Sulfides are the sulfur analog of an ether with a sulfur atom with two alkyl groups attached. And what we learned with sulfides is that they are borderline nucleophiles, meaning they're on the border between strong nucleophiles and weak nucleophiles. So they will act as strong nucleophiles, but only with primary alkyl halides. You will only have SN2 reactions between sulfides and primary alkyl halides. And we saw an example of that. We showed examples in class. We also showed the synthesis of SAM, or S-adenosylmethionine, a key reagent used in biosynthesis in nature that was formed by one of these SN2 reactions of a sulfide with a primary leaving group. Okay, so not a whole lot on these compounds, but the things we learned are important. And then finally, we finished our chapter with epoxide ring opening. So because epoxides have ring strain or angle strain, they can undergo these ring opening reactions. And there are two types of these reactions. We have strong nucleophiles, and those ring openings proceed via SN2 reactions. So we have inversion, we have attack at the less substituted carbon. When we're using strong nucleophiles to open epoxides, we have to protonate the oxygen in a separate step. We have to add water in a second step. It's important to separate those two steps. And then the other method of epoxide ring opening involved the use of HX. So here we're inverting the order of the steps. We protonate the oxygen to the epoxide first. Then our halide nucleophile comes in second. And we referred to this as an SN1.5 reaction, not an official term, but a substitution that has elements of SN1 and elements of SN2. It proceeds by inversion. That's the SN2-like property. But the nucleophile attacks the more substituted carbon. That's the SN1-like property. And we gave an explanation in class about the bond breaking being more advanced than the bond making, giving a partial positive charge on a carbon at the transition state. And we've used that same explanation for two other reactions that we've learned subsequently in chapter 10. So that's an important one to understand. Finally, we can also use sulfuric acid and water or an alcohol, and the same thing happens. We just use the alcohol or the water as a nucleophile. We either get a diol or an ether as the product of this reaction, but it follows the same mechanism as the HX ring opening. All right, so that is everything from chapter 9, one of our longer chapters. So we'll erase the board now. Okay, so now we're ready to start chapter 10, alkenes. So we began with nomenclature. The key things with alkene nomenclature, we have the -ene suffix. We learned that alkenes have a lower priority than alcohols, but a higher priority than alkyl halides or other substituents that are just named as part of the prefix. A second thing we learned that's important with the nomenclature of alkenes is the EZ system. Since we've learned about alkenes in previous chapters, we learned the cis and trans nomenclature system. But in this chapter, we learned that there are some limitations. There are some alkenes where the cis and trans nomenclature doesn't work. And so we have the EZ system, E meaning entgegen or opposite, Z meaning zusammen or together, for naming alkenes that can have diastereomers. Okay. We talked about physical properties of alkenes, and the key thing here was learning that cis alkenes are slightly polar, whereas trans alkenes are not. We talked about why that was the case and the impact that has on the boiling points of these compounds. So understanding why cis alkenes have a very small dipole moment is important. As we did in our last chapter, we talked about interesting compounds, interesting alkenes, and the case where we tied the structure of the compound to either the function or the physical properties was with the fatty acids. So we talked about saturated and unsaturated fatty acids, both of which occur in nature. And we talked about how the unsaturated fatty acids or the oils have lower melting points than the saturated fatty acids, also known as fats. So you should be able to explain why the unsaturated compounds have lower melting points than the saturated ones. Okay. So from there, we'd already learned how to make alkenes, so we didn't spend a lot of time on that. So the remainder of the chapter was spent on reactions of alkenes, which are all addition reactions. The first one we had was the hydrohalogenation. The hydrohalogenation reaction involves the addition of HX to an alkene. So for all of the addition reactions we learned in chapter 10, it's important to understand the regiochemistry, meaning to which carbon does the proton add and to which carbon does the other group, in this case the halide, add. So we have regiochemistry associated with the reactions in this section. And we also have stereochemistry associated with them, the types of addition. We have syn additions and anti-additions and mixtures of both, okay? So with the hydrohalogenation, we learned that it follows Markovnikov's rule. That's associated with regiochemistry. That's telling us that we end up with the more substituted alkyl halide as opposed to the less substituted alkyl halide. And we explained why that is the case in class. We have a carbocation intermediate. The more substituted carbocation is formed faster according to Hammond's postulate. And so the halide ion will then attack that more substituted carbocation to give us the product. And then we also learned about the stereochemistry, a mixture of syn and anti-addition. Okay, so both syn and anti-addition occur in hydrohalogenation reactions. We have a carbocation, so we obtain rearrangements, or we can observe rearrangements in these reactions because of the carbocation. And then there was a little bit of additional information on stereochemistry that I gave you in class. So we're going to go ahead and show you a figure that we showed in class. This figure was not in the book. It was in earlier editions of the book, but unfortunately they took it out when they made the edition of the book that we use in class. So we'll come up in just a second, hopefully, once the projector gets warmed up. Okay, here we are. So remember, we said that when this alkene here is protonated by HCl, we're actually forming a stereocenter in that process. And so we generate a chiral carbocation. Of course, the positively charged carbon is not a stereocenter, but the other carbon, the one that gets protonated, is a stereocenter. And so we produce enantiomers because this alkene is protonated from above and below at the same rate. But then when the chloride attacks the carbocation, because this carbocation is chiral, it is more hindered on one side versus the other. And so we said that the one on the left, the chloride approaches from the bottom faster than it approaches from above, meaning that A is major over B. And that's fine because these are diastereomers. And then we said with this carbocation, the chloride approaches from the top faster than the bottom, meaning that D is major over C. So we went over that in more detail in class. I'm not going to go into the detail now, but it is important to understand this principle, to understand that although the products will be formed racemic because the carbocation is chiral in this case, when we form this second stereocenter, that is formed in a diastereoselective process with a major diastereomer and a minor diastereomer. So that was not mentioned in the book, unfortunately, but it is an important point that we need to understand. Okay, so with that, we'll turn that off, go back to the board. And look at our next reaction, which was the hydration of alkenes. So in a hydration reaction, it's going to be a very similar mechanism to a hydrohalogenation, but we use sulfuric acid as opposed to HX. So in this case, the conjugate base of sulfuric acid is not a nucleophile. So the water that we use in this reaction acts as the nucleophile instead. So since the mechanism is virtually identical to the mechanism of hydrohalogenation, we have the same principles. We follow Markovnikov's rule. We obtain the Morse substituted alcohol. We have a mixture of syn and anti-addition. We can have rearrangements. But there was another principle we learned here. This is a reversible reaction. It's the reverse of the dehydration that we learned in chapter 9. And so we learned the principle of microscopic reversibility. This principle told us that in an equilibrium process or a reversible reaction, the same intermediates and transition states are encountered in either direction. So once we know the mechanism of the dehydration, we also know the mechanism of the hydration. We're encountering the same intermediates, just in the opposite order. Okay, so that can help us in learning mechanisms. If you know the dehydration mechanism really well, then you would know the hydration mechanism also. Okay. Next up, we had halogenation. And in a halogenation reaction, we can only use bromine or chlorine. Fluorine is too reactive and iodine is not reactive enough. So this reaction has a different mechanism than our hydrohalogenation and hydration than our other additions we'd learned to this point. We form a halonium ion as our key intermediate in this reaction. Okay. And because we form a halonium ion instead of a carbocation, there are no rearrangements. You should know why the halonium ion forms instead of the carbocation. We went over that in class. It's more stable than the carbocation, and we talked about why that's the case. And then we learned, because it's a halonium ion intermediate and not a carbocation, and that intermediate undergoes ring opening with inversion, the net result is we have anti-addition in a halogenation, as opposed to the syn and anti-addition that we see in hydrohalogenation and hydration. And then we learned the term stereospecific in association with this reaction. And we learned that with two alkenes. We showed you a figure where cis-2-butene gave one diastereomer, I believe it was the chiral dihalide, and then trans-2-butene gave a mesodihalide. But a stereospecific reaction is one in which one diastereomer of the starting material gives one stereoisomer of the product. The other diastereomer of the starting material gives the other stereoisomer of the product. So that's a term we introduced with halogenations. And then we learned a closely related reaction, halohydrin formation. So in halohydrin formation, we're using, again, chlorine or bromine, but we're adding water in this case. And because we use a large excess of water, typically as a co-solvent in this reaction, it's able to open that key halonium ion intermediate instead of, in preference to the halides, which are present in much lower concentrations. Okay. We also had an alternative set of conditions that we could use. We could use N-bromosuccinimide in aqueous DMSO if we wanted to avoid the stinky bromine if we're making a bromohydrin. Okay, so almost the same mechanism as halogenation. We do have a third step. We have to deprotonate the oxygen at the end of the reaction using another equivalent of the water in this case. A key issue for halohydrin formation that does not appear in halogenation, since we're adding two different groups to the alkene, we need to know which one will end up on the more substituted carbon and which one ends up on the less substituted carbon. And what we learned with halohydrin formation is that we obtain the more substituted alcohol. So what that tells us is that the water in the second step of the mechanism attacks the more substituted carbon of our halonium ion. And the reason for that is the same as why when you use acid to open an epoxide, the nucleophile attacks the more substituted carbon of the epoxide. So this is another one of those SN1.5 reactions. It proceeds by inversion. We only have anti-addition, but the nucleophile attacks the more substituted carbon because the bond breaking is more advanced than the bond making at the transition state. Okay, and then we learned why this was important. We learned that halohydrins are precursors to epoxides. Okay. All right, and then our fifth and final addition reaction we learned is the hydroboration oxidation. So there were some differences here. The hydroboration oxidation converts alkenes into alcohols, similar to the hydration, but there are differences in mechanism and therefore differences in the products that one obtains. One obtains the less substituted alcohol from this reaction. So it does not follow Markovnikov's rule. We also have syn addition only. Okay. So we proposed a mechanism that was consistent with these two principles, and that is the concerted mechanism, one-step mechanism with no intermediate, a force-centered transition state, and then we use that mechanism to explain why we obtain the less substituted alcohol, why the reaction only gives us syn addition. So you should be able to explain that. There's a steric explanation and an electronic explanation. Both are important to understand. And there's a figure in the book that shows it very nicely. We also learned about bulky organoboranes. The formula R2BH, 9BBN is an abbreviation for a bulky organoborane. We said that these could be used to increase the selectivity for the less substituted alcohol. The less substituted alcohol will always be your major product, but if you're using BH3, you might not get a great ratio. So if you want a bigger ratio favoring the less substituted alcohol, you can use a bulkier organoborane. And then we spent most of the time talking about the hydroboration step. As for the oxidation, we just learned the reagents, hydrogen peroxide and hydroxide, but we learned about the stereochemistry. This oxidation step precedes with retention of configuration. So when you have syn addition plus retention, the net result is a syn addition of water across the alkene. Okay, so that sums up chapter 10. So we'll go ahead and erase the board and then go on to chapter 11. Okay, chapter 11 is on alkynes. At this point, we've barely started this chapter, so a lot of what I'm going to outline for you are topics that we will cover on Wednesday and Friday. So alkynes have many similarities to alkenes, which is why the two chapters come one right after the other. So many of the principles we learned in chapter 10 will help us understand alkynes, so we don't really need to spend as much time on them. We learned a little bit about physical properties of alkynes. The key thing here, we learned that the pi electrons are held more loosely than the pi electrons in alkenes. We used bond dissociation energies to indicate that those pi bonds are not as strong in alkynes compared to alkenes. So the pi electrons are not held as tightly. And so we said that alkynes are more polarizable than alkenes. That's the consequence of this. We'll spend a little bit of time with nomenclature. The key thing to note here is we have a suffix of "-ine". We also have equal priority with alkenes. So the naming of alkynes is very similar to alkenes. So we'll just spend a little bit of time on that on Wednesday. The preparation of alkynes is something that we learned previously back in chapter 8. We have to perform a double dehydrohalogenation. Okay. So this is 2 consecutive E2 reactions. So it requires a vicinal dihalide or a geminal dihalide. We know how to make vicinal dihalides from halogenation of alkenes. But this reaction requires a very strong base. That second E2 reaction requires a stronger base than a standard dehydrohalogenation. So we taught you in chapter 8, you needed 2 equivalents of sodium amide or sodium hydride, one of these 2 bases, for this reaction. Okay? So the reactions of alkynes, the first 4 that we'll discuss in this chapter are going to parallel the reactions of alkenes because they will be addition reactions. So we'll start with the addition of HX. And we're going to need 2 equivalents of HX. If we use 1 equivalent, we're going to form a vinyl halide intermediate. Okay. And then when we add our second equivalent of HX would convert the vinyl halide intermediate into the dihalide product of this reaction. Okay. So a couple of points. We will follow Markovnikov's rule in this reaction. The mechanism we'll learn in class is going to be different from the mechanism in the book. So this is an important thing to pay attention to on Wednesday when we discuss this. The mechanism in the book involves a vinyl carbocation, which the book has told you in an earlier chapter is too high in energy to exist. So it's kind of inconsistent to have a mechanism involving a vinyl carbocation. There's a better mechanism for this reaction, and that's the one we're going to learn in class. It's a little more complicated, but it makes more sense. So it will be important to discuss. It's the only mechanism I can remember that we'll learn in class that actually involves 3 molecules colliding simultaneously, but it allows us to avoid the formation of a very, very high energy vinyl carbocation. Okay? And then another thing we'll learn in this mechanism is that in the second part of the mechanism, there's a resonance stabilized carbocation. And that's what determines which of the possible products is formed in the reaction. Okay? So these points we'll go over on Wednesday in class. So we also have a halogenation reaction of alkynes. And so that halogenation reaction, if we add 2 equivalents of chlorine or bromine to an alkyne, we're going to generate a tetrahalide product with 2 halogens on the adjacent carbons. If we used 1 equivalent, we'd have a dihalide intermediate, we'd have anti-addition, and we would have a trans dihalide. Okay? So knowing what the intermediate would look like in both of these reactions is important. What you would get if you used only 1 equivalent of the halogen or the HX versus the product you would get if you use 2 equivalents of the halogen or the HX. Hydration, the addition of water to an alkyne. A couple of differences exist between hydration of alkenes and hydration of alkynes. With alkynes, mercury sulfate, HgSO4, is going to be required. The book is kind of ambiguous on this point. It says you use it with terminal alkynes, but not necessarily with internal alkynes, but you could if you wanted to. We're just going to be unambiguous and say you want to use mercury sulfate every time you're performing a hydration of an alkyne. Okay, so mercury sulfate is required. When we add water to an alkyne, the intermediate we get is called an enol. We actually introduced that term in chapter 9. An enol is when you have an OH group attached to the sp2 carbon of an alkene. And enols will undergo a process called tautomerization to generate ketones. Okay, and so we're going to learn a term called tautomerization. We're also going to discuss this on Wednesday. This is when you have an equilibrium between 2 constitutional isomers. So in the hydration of an alkyne, you form an enol, but that's not your final product. It will very rapidly convert into a ketone. We'll make that singular so that it's consistent with the enol. Okay, and then also here, there's going to be a different mechanism from the book. In the hydration reaction, the book also shows you a mechanism involving a vinyl carbocation. And they don't use the mercury. They say you have to use mercury sometimes, but they don't use the mercury in the mechanism. So we're going to show you a mechanism that uses the mercury that allows us to avoid forming that high energy carbocation. Again, it's a bit more complicated than the one in the book, but it makes more sense. So it's going to be more valuable to us because it will help us understand the reaction better. Okay, and then the last addition reaction we have of alkynes is hydroboration oxidation. And what's going to happen here, we know that when we perform a hydroboration oxidation of an alkene, we obtain the less substituted alcohol. And the same thing happens with alkynes. If we're doing this reaction on a terminal alkyne, we will get the less substituted enol. And then what we'll find is that will convert into an aldehyde as opposed to a ketone. Okay, and we'll talk about that. We'll get to that on Friday. Okay, and then the last reaction of alkynes that we'll learn involves acetylide ions. We briefly mentioned acetylide ions on Monday. We know that our alkynes are the strongest acids of our hydrocarbons, and we should understand why that is the case. We learned that back in chapter 2, related to the hybridization effect in acidity. And so we know that to deprotonate a terminal alkyne, we need a very strong base. So a very strong base will react with a terminal alkyne to remove that proton and generate an acetylide ion. Okay? And so what that means is that the acetylide ion itself is a very strong base. It's a very strong base and a strong nucleophile. And so what that means is that we can use acetylide ions in SN2 reactions, but only with primary alkyl halides. Okay? Because of the fact that it has very strong basicity, an acetylide ion will promote elimination with secondary alkyl halides as well as tertiary. So SN2 reactions only with primary alkyl halides, but then you can also perform epoxide ring openings with acetylide ions. Because it's a strong nucleophile, you're going to open the epoxide at the less substituted carbon in the SN2 process. So these reactions are very, very important because they allow us to form carbon-carbon bonds. Most of the reactions we've been learning so far are enabling carbon-hydrogen or carbon heteroatom bond formation. We haven't really learned reactions that allow us to form carbon-carbon bonds. Carbon-carbon bond forming reactions are vital because they allow us to make longer chains from smaller building blocks. So I'll give you a big hint. If you are asked to synthesize a molecule that has more carbons than the starting materials you are allowed to use, that tells you that you will have to use a carbon-carbon bond forming reaction in that synthesis, meaning that you will have to generate an acetylide ion and then perform either an SN2 reaction with a primary alkyl halide or a ring opening with an epoxide. So these are very important reactions, our first real carbon-carbon bond forming reactions that we've learned in the class. Then the conclusion of chapter 11 involves talking about multi-step synthesis, or how we would design a synthesis of a complex target compound from simpler starting materials, a synthesis that would have to be accomplished in more than one step. And as we'll learn, to plan a multi-step synthesis, it's almost always easier to work backwards, to look at the target compound and ask ourselves, what precursor could make this target compound in one step? And then you take that precursor. How can I make this compound in one step? And you work backwards to the starting materials that you are allowed to use in the reaction. And that process is called retrosynthetic analysis. So you want to make sure you practice that by doing the multi-step synthesis homework problems. Even though we haven't discussed this process yet, you've learned enough reactions that you can actually do multi-step synthesis problems. And so I encourage you not to wait until Friday to address this, but to start now and practice these problems. All right, so that concludes our review for exam 3.